delicate deformable objects. We have three speakers because Frédéric Coledani could not be available today. So we had first Farshid Alambeigi from UT Austin, followed by Fanny Ficuciello from University of Napoli in Italy, speaking also on behalf of Bruno Siciliano, and we conclude with Wenzhen Yuan from Carnegie Mellon, US. So first, each one of you will speak for 5 minutes and introducing their respective expertise and works in the field of deformable object manipulation. And after this, we will have an interactive discussion. So this will last half an hour. It's a bit what we really focused our workshop on. In fact, we think that, so you should know that there were many proposals on this topic at IROS, and we were lucky enough to have our accepted. And we think that it's also because we pushed a lot of the interaction. So in contrast with classical workshops, we want you to discuss, and we want to discuss with you about some technical and we call them more personal questions, although they are still focused on research. And the technical questions are listed on this slide, so maybe you had time to look at it before, and otherwise I'm sure you will improvise very well on the discussion. So this said, I will now again keep my screen shared because I will, Farshid, I will present from here.
Thank you so much.
Not a problem at all.
Hello, everyone. I'm Farshid Alambeigi. Thanks so much, for the organizers for having this wonderful and new and novel, basically, workshop. Thanks for the invitation. Next slide, please. So I'm Farshid Alambeigi. I'm an assistant professor in the University of Texas at Austin. So I joined UT in 2019, September of 2019. It's about a year I'm here in the UT. So my background is surgical robotics. I'm working like about more than 10 years I'm in this field. So working in different types of surgical robotics application. My expertise is mainly in developing different types of continuum robots from the hardware, to shape sensing and control. Also, one of my interests is surgical autonomy. So I recently graduated from Johns Hopkins and then joined to UT. Can you go to the, okay. I think it's working if I don't jinx it. Okay. So this slide, particularly I'm showing, the work that I have done on autonomous surgery. It's fine. I think this is as a timing. That's my issue, actually. So let me just talk about like the, general work. So you see in this slide, I have worked mainly with Da Vinci surgical robots, basically DVRK. We did multiple research to do autonomous, basically manipulation of different types of basically deformable objects, from homogeneous to heterogeneous objects. By heterogeneity, we meant, the mass of the objects, the density and type of that can be very different, can dynamically change. And then the goal here was that without knowing the deformation behavior of a real phantom, as you can see here, from a lever to like a phantoms that we made, we wanted to autonomously manipulate and learn without having a prior knowledge and on the fly the deformation behavior of an object. For instance, on the right, you see this is a lamp lever. The geometry is very heterogeneous and 3D. And the goal here was that without having any prior knowledge, we wanted to know, like the robot can learn the deformation behavior and manipulate one specific point on the objects to one particular point. And as you can see, during the manipulation, we wanted to also disturb it with an unknown disturbance. You see, the robot is trying to match 2 points, and then I'm just trying to disturb the robot with different types of work. So like on the left, this is like a basically lamb kidney, right? Lamb liver, to show that the algorithm is actually very generic and versatile and can learn without having a knowledge on the deformation behavior of the object. If you can go to the next slide, actually, as I said, besides actually working on autonomy on deformable objects, I also work, one of my interests is continuum robots or flexible robots, basically from the fabrication to control and basically shape sensing. So you see in this slide, what we are doing, we have made a 3mm small continuum robot back in Hopkins for head and neck surgery. The goal here was that, again, and similar to soft tissues, continuum robots are, we can count them as a deformable objects, right? Because they can deform. So here our goal was that without knowing any deformation behavior on the objects, both in free environment and obstacle, like obstructed environment, we wanted to control both shape and basically position of the robot. Again, this robot, if you can see, it has backlash, friction, it's a cable-driven robot, and modeling this robot, as you know, is pretty hard. So the goal here was that, can we, without knowing the real deformation behavior of a robot, specifically continuum robot, can we control it? So in free bending, you saw that position and shape is very easy. Then we went one step further, said, let's move the robot in an obstructed environment and it's colliding with obstacle that basically the robot doesn't know an obstacle is in the environment. And then geometry of the obstacle can be flat and it can have different types of basically stiffness. It can be soft, it can be hard. And you see here, that's a book. The robot actually doesn't know there is an basically obstacle while it's moving from green to red. And if you see the basically plots that we have on the right, the bottom right, you see change of the deformation behavior that we are learning on the fly. And I show that here I'm showing different types of basically convex and concave environment. This is like another soft environment. You see the robot goes and pushes to the environment, which it doesn't know about its property and location. And after some poke realizes that's not the best way and finds another basically a trajectory to the real target. This is a ball again. It's like a concave actually obstacle, which makes it harder. And this was the most interesting one. So this is an Amazon package that basically we have air trapped inside that package. You know that if you are pushing out up to some certain point, it's soft and it becomes very stiff. So another basically type of work was we wanted to manipulate the deformable objects with a deformable robot. You see here we have two sorts of uncertainty. Both of the robots and the object, they are unknown, the deformability is unknown, and we are actually in this work learning on the fly the formation of both robots and the object simultaneously to manipulate the object. And this is an like a ex vivo test. We did like a lamp hard to see that basically the interaction is safe, and then we can control the robot from one specific point to the basic and other desired points. To summarize, I think this was the last slide. What I have done, we look at both continuum robots and deformable objects, basically deformable tissues as deformable objects, because both of them are sharing unknown deformation behavior. So we have developed algorithms that we can learn this deformation like on the fly and without having any prior knowledge for surgical robotics. Thanks.
Thanks a lot, Farshid. Sorry for the inconvenience.
Not a problem.
So, hopefully the next talk will be smoother because Fanny Ficuciello will present from her laptop, I guess. So
yes, I'm going to share the screen. Can you see my screen? Can you see it?
Yes, we can.
Okay. So I switch to the presentation mode. Can you see the presentation mode?
Yes.
Okay. So, everyone, I'm Fanny Ficuciello, Assistant Professor of Control and Robotics at University of Naples. Our in manipulation in general in soft robotics. that we are conducting at Prisma Lab and Icarus Center. As you may know, Prisma Lab is the historical robotics research group of University of Naples. Icarus is a novel interdepartmental research center that is focused on surgical robotics and which was founded a few years ago. So first of all, I will present some results on our research on manipulation of 3D soft objects. So managing deformation is an important issue if we want robots to act in human environments and perform human-like tasks. So what we developed is a method for dexterous manipulation of 3D soft objects for real-time deformation control. This work has been done in cooperation with INRIA and in particular with Professor Christian Durier. So the method is based on finite modeling, and actually the goal is to compute the desired contact forces on selected points on the object where are placed the fingertips of the hand. So basically those points are called actuators, starting from the desired deformation of different points that are dislocated on the object that are called effectors. So basically, to find the desired forces, we start from a desired deformation and we solve an inverse FEM simulation. And from the forces, we can then compute the displacement, the desired displacement of the robotic. So the experiments are applied to an anthropomorphic hand that is underactuated and that is manipulating a soft cylindrical object. So actually, in order to improve the model, we estimate the elastic parameters of the model, so namely the Young modulus and the Poisson ratio. So in order to estimate those parameters, we use Nilder method offline, and we use a contact force sensor and an RGB camera. So basically, we try to minimize the error between, so the displacement between the simulation of the deformation that are obtained using FEM models and starting from the information of the contact force, and the measured deformation that are acquired by the RGBD camera. So in this way, we can estimate the Young modulus and Poisson ratio that we will simulator. So the results are interesting because actually we found out that we measured all the real deformation of the object using markers on the object and an external camera, and we compared the deformation of the object to the desired one. And we found out that we have two sources of errors. One, of course, is due to the underactuation of the hand, but this is actually a problem that is external to our proposal, and is due to the simulation, simulation. And actually, this is the smallest error, the smaller error, because it's less than 1 millimeter. So this means that the model that we used is efficient, as well as the estimation of the elastic model parameter. Besides manipulation of soft objects, actually we are also working on soft hands, soft surgical tools, and soft robots. About these anthropomorphic hands, our insight is the realization of a particular joint for those hands that is called core joint, that is a compliant rolling contact element that is obtained by means of a base link and a distal link that are stuck together using elastic ligaments. And then to move the distal link with respect to the base link, we use a tendon. And for each finger, we have one tendon that moves 3 joints that are the joints and the proximal interphalangeal joints. And the shape of the links are designed in order to have the metaphalangeal joints faster with respect to the other one, so we can obtain. Thanks to this intrinsic elasticity, the hand is able also to perform manipulation tasks, as you can see in the video. Using an underactuated hand, because the hand is moved by 3 motors. A similar concept has been used also for surgical tools that we have tested on the Da Vinci robot. So the tool is composed by 3 fingers, and each finger is obtained by means of vertebrae, and the motion, the actuation system is obtained by means of nitinol tendons. So basically, the hand show good grasping and manipulation capabilities, but at the same time, it is also compliant with respect to external interaction. So interact with the human body and organs. So this is important for safety, but also the compliance allows also grasp easier and to have a better manipulation of the tissues and organs. And another project that we are developing is depicted on the right of the slide. So we have a video here that actually is a simulation of a robot that is constituted by a rigid part and a soft part. So this robot is designed for prostate biopsy. The idea is to use a soft part in order to reduce the number of motors that we have to introduce in the design. So instead of using 6 motors, we can use 4 motors. This means that we can have a lightweight robot, and also the safety during interaction increase using a deformable part. Of course, introducing a soft part led to a complex control problem. So we have to deal with precise motion of the robot. We need precise positioning of the needle for prostate biopsy. And to handle this issue, we are thinking to different solutions to sensorize the soft part. In particular, we are working on liquid metal-based sensors in order to measure the deformation and to precisely control the robot. So this is part of the work that we are developing in our lab. I thank you for your attention. I can stop sharing.
Thanks a lot, Fanny. So Wenzhen is next. You need to turn on your microphone.
Okay, give me 1 second. I would like to share my screen.
Andrea, I think she crashed out. Okay.
So does things work now?
Yes, perfect.
Okay, good. So thanks for the invitation. I will talk more on the sensing side instead of on the manipulation side. So a brief introduction about myself. My name is Wenzhen Yuan. I'm an assistant professor at Carnegie Mellon University, and my research interest is on tactile sensing for robots. So I will probably talk a little bit from the other perspective about soft object manipulation from the sensing perspective. So specifically, I'm going to talk about my work estimating the hardness levels of objects. So firstly, let's take a quick look about the sensor I've been working with. It's called GelSight. Look like this. So, oops. It's in short, it's a high resolution and soft tactile sensor. It's a vision-based sensor and using optical design so that it is able to provide very fine detailed information about the contact geometry as well as the contact force. So here is an example of how it works. So here we ask a human to take the sensor and press on different objects on different locations. So the middle images here shows the raw output from the sensor. So that you can see there's some change over the background color, which is directly related to the contact geometry. And also there are some black markers painted on the surface, and we track their motions. And that tells about the information about the contact force and torque. So specifically, if you can see the markers are moving to one direction, that indicates there are lots of shear force on the contact location, contact area. Or in very rare case here, you can see the markers are only spreading out. So that means there's only some normal force. So also are able to put our sensors on robot fingers so that we can ask the robot to grasp and manipulate different objects. And while during the process, we are able to get those fine information about the contact surface. Okay, so let's look at this case. A human is pressing a GelSight sensor on objects. And as we just let's through the slides, we know that our sensor is able to measure the very high resolution geometrical information about the contact objects. And that is based on the deformation of the sensor, because the sensor has a soft interface. But in other case, the object may be soft as well. So during the contact, not only the sensor deforms, but also the object deforms. And if the object has different hardness level, the deformation level will be different and the force level is different. And that is something exactly what we can measure from the sensor. So here shows an example about what happens during this kind of contact when a human is pressing these sensors on this hemispherical shape. So if you are not only looking at the geometry from the color, so this window shows what we see. So you can see this is a round area, it keeps spreading because the contact area is always like a part of the hemispherical shape. So in the other case, we can press our sensor on the other object, which is of exactly the same shape, but is much softer. So as just shown here, we expect there will be a much larger deformation of the objects. And if you look at the sensory output from the GelSight sensor this time, so you can see that it's still a round area, but the contact area is much larger and the color is softer. So that means the surface normal or surface gradient of the contact surface is much smaller than the previous case. So considering the objects, the original shape of the object is exactly the same. So this means this new object is much more softer. So of course, we can take a look at the marker's motion, which indicates the contact force. So here it shows an examples of several frames from a pressing sequence we get from the sensor. So on one hand, we can see the markers moves much less when we're pressing on a soft case. And also if we extract how the color changes over the progress, we can also see the color is more dimmer for the soft objects. So this means we have different response over both geometry deformation and the contact force. So this actually matches very well because we can stem this from the physical model of the objects about like how some object deforms, so that we can fit regression models to measure the dynamic relationship between how this color changes, contact area changes, and how marker motion changes over this press sequence. And that can tell us a good estimation about hardness of the objects. And the constraints about this is that we do have, it works great on those spherical objects with no diameter. That means we have some pre-knowledge about what the original shape of the object is. So we can just use some database methods to fit these simple regression models. But the things become more challenging if we want to work with more arbitrary objects. Example like I took the example of avocado because that's a good example of how humans estimate arbitrary objects with hardness. And well, this hardness information is very important for us to understand. For example, here is we want to know whether this avocado is ripe or not. So how does this work? The good thing is that the physical base still exists here, that when we use our sensor to contact a soft objects, the deformation is larger while the force is smaller. But the only challenge here is how to build the modeling. So we rely on deep learning for building this model. So firstly, we need to collect a very large data set. So I collect a data set of using silicon to cast into different shapes with different hardness level, and use our gel size sensor to trace on the surface either by a human or by a robot. And then we collect a large data set and then use the data set to train a combination neural network of CAN and RAN. And finally, we are able to estimate the hardness of an object with arbitrary hardness. So specifically, this is something what we really want our robot to be able to do. So they estimated the hardness of an avocado. So here we don't really have a ground truth about how hard an avocado is. So we just rank 2 avocados from soft to hard according to human perception. And then we use gel size to press on the surface to gather a sequence of the contact information and then estimate the hardness level from that. Okay, so that's the end of my presentations. Oops, how can I go on? So a short summary. So we propose a method of estimating the hardness of the objects according to the deformation level and the contact force. And we use a high resolution tactile sensor to measure the deformation and force and train a database methods model to estimate that. So that's it. Thank you.
Thanks a lot, Wenzhen. Very interesting. I enjoyed all 3 talks, although I was a bit familiar with your research. For the 3 of you, I must admit it was very nice to hear you talk and present this. So we have not so much time left. We have about 20 minutes. So I would like to launch this panel by asking some questions, but please feel free to extrapolate on the questions. So so I just filtered a bit all the questions we sent out first. One thing I would like to know is because we have different views here, so I think we've seen more work on design. On the gripper from Fanny and the sensing from Wenzhen, and also a control. We've seen different approaches from Fanny and Alambeigi as well. So what do you think is more important to manipulate a soft object? Do you think we should more work on designing adapted the grippers or more on control strategies? So you can feel free to speak.
I can answer first. So in my opinion, are both important because the physical interaction in robotics is an essential issue. So to have a robot that has a good mechatronic that is compliant and that is good for interaction is a very important point. Of course, depending on the mechatronic design, you will have other control problems that should be addressed. But I think that the 2 issues work together. And in order to improve human-robot interaction, especially dealing with deformable objects, deformable environments, and also delicate objects like organs or tissues in surgical robotics, we really need to a good design, so a proper design, and also good control.
I think we lost the end.
Here still? Can you
Thank you,
hear
Fanny.
me?
Yes. Thanks a lot.
Yeah, I mean, I have like my opinion is similar to Fanny. Like, of course, I mean, similar to other real world like problems. Doesn't matter it's deformable objects or hard objects. To like accomplish a successful control task, we need the three elements. We need a good hardware, we need a good sensing system, and we need a basically good like control algorithm, right? So without any one of these ingredients, a successful control would be like very hard. So let's say you have a very bad like mechanical system. Even you are an expert in control, you never can control it successfully. The same goes with sensing. Like, let's say, as Fanny mentioned, for surgical robotics specifically, we have limitations in terms of other constraints, in terms of design and fabrication, because we have safety and sterilization on the side. So not other sensors available or like control algorithms are typically working on other application is basically working for this specific task. So to my opinion, to summarize, all ingredients are important to have a successful, basically, control task.
Thank you.
Yeah, I agree. I think like all the parts like a good perception system, a good control strategies, and also a good design of mechanical parts are all important. It also highly depends on what kind of task it is. So I noticed like the task I presented and the task of Fanny and Facade presents are pretty different. Like the objects I'm working with are like overall deformed, like a big chunk of objects, and we're trying to figure out like what happens when we grasp them or contact with them. While I see the other presenters are working more with like some objects that are like not locally deformable a lot, but like globally can do have lots of deformation. So I expect there shall be different strategies and different emphasis when we are dealing with different cases.
Yeah, this leads to another question which I have. Well, we've had a lot while we brainstormed while organizing this workshop, which is, as I think you just said, it depends on the application. So what we have confronted with while we were doing our research was with the fact that it seems like we do a workshop about manipulating deformable objects, but then it turns out that the methods and approaches depend a lot on what you're deforming and how you do it and what the application is. So as you just said, if you touch an avocado, it's different from the medical world. So one thing we wonder more and more, because we are in a stage where we see some things that start to work, but they're very application specific, is then here I really want an honest answer. Do you think, I mean, I'm not saying the previous one was not honest, but I would really say, do you have the feeling that it is possible to have some sort of general framework for deforming objects, or is it all dependent on the type of object and the setup and the application?
If I can answer, I think that yes, a common should be modeling. So model deformation can be something that can be shared in different fields, and so how to represent the shape of an object and how to actually represent the dynamics of the deformation. So this is something that I think can be shared among surgical robotics, manipulation, and other fields. So all the modeling part and maybe something also about perception, of course, can be. So I think that methods can be shared among different fields. I don't know what the other speakers think about this.
So I think that's a nice idea. I got the point what Fanny is saying, because each of the researchers like around the world working on a specific problem, there are some consensus regarding that, people sharing their experiments to make, like, let's say we want to use like a machine learning algorithm. By sharing this knowledge, it would be very helpful among other communities. So my actually perspective is a little bit like different. Like, as you saw, like, the experiments that I did, my idea was that, like, exactly try to answer the question you said. Is there like any generic algorithm that we can basically implement on different type of tasks, specifically surgical robotics, no matter it's a continuum robot, which is an flexible object, or a deformable tissue, or it's another deformable object, can be developed like an algorithm that we can basically generally learn the deformation behavior without having the prior knowledge. As Fanny mentioned, her work mainly, they try to use finite element applications and then detect the modeling and use that model-based algorithms to control the robot. But my main issue for surgical robotic is that, like, your body, my body, the tissues, different organs, they have different properties. So it's pretty hard. It's very difficult. Specifically, these tissues are viscoelastic. As soon as you touch them, the deformation changes. So we need to look for like adaptive or online algorithms, no matter it's machine learning or thanks to classic control algorithms or other algorithms or mix of these two. We need to look for methods that can learn and adapt this deformation behavior, and then like a complementary control algorithm that can use this learned model to iteratively control basically the robot. Because to me, it's pretty hard to rely on offline model-based methods to perform a successful deformable object manipulation, no matter it's like continuum robot or like deformable tissue.
Yeah, I totally agree with that. It might be hard to find a very general model for all the deformable objects manipulation, but I think it's possible to put things in several categories, and we should be able to find lots of common things among each category. So, for example, I will put things into this. So one category is on the examples I'm working on, like working with the bulk objects, which is like according to the materials itself or according to its structure that is deformable. So, for example, the motivation I started this project is actually from grasping. So the other day I visited the other lab working on grasping, and so they're using a robot, just a parallel gel gripper, to squeeze on the object and grasping things, which is a pretty traditional way of doing grasping in the field. But one thing I noticed is that they also have some soft objects like stuffed animals in their data set. And they still have the same presumptions of grasping force, and which end up like squeezing the stuffed animal to something very large deformation, which I think like is not a human how humans do things. It's not how we expect the grasp happens, especially with those kind of soft objects. So that's why I was thinking that how can we get some feedback? How can we get some estimation about what is a proper grasping force? Where shall we start when we grasping some deformable objects? So this is where I start this project and use our sensor to estimate the deformation, or it's actually the surface deformation during this increasing contact. So I will put, for example, this into one category. So another case I would think very commonly in several groups is on manipulating ropes or folding clothes. So that is the kind of object, like if you consider the material, it's a fabric or a very sliced piece of the rope. So I don't think that the material itself is deformable, but if you put them into a large structure, the structure is deformable. So I guess the challenge for manipulation of that case is like, how can you model the overall motion of the objects? How can you model the relationship between the motion or action of the robot with the overall deformation of the objects? In that particular case, like I don't think my method here will be very helpful, because what tactile sensing can provide is only a local information about what the local deformation is like. So for that category, they need another modeling of their objects. So the third case, I guess, I'm just learning recently from Farshid and Fanny is, I guess, is the deformable tissue. It's like the combination of the two. The material itself is deformable. When you squeeze on the grasping point, it may get thinner. But also, I think the most important to you is how the global shape deforms. Especially in your case, it's more challenging than the clothes because for the clothes, the material doesn't stretch a lot, but in your case, the objects also stretch. So I think there should be another modeling, but also we can take lots of experience from the other aspects as well. So, and I also agree that I think by looking into the application, they will provide lots of insights about what do we really want to look into those objects for manipulation and what do we really want to achieve.
Yeah, actually, I want just to add something. I mean, I don't think that can solve different problems among fields, but for me, to control shape and motion of soft objects, you need modules that are deformation modeling. That means that include shape representation, dynamics, and learning parameters of the model. Then you need simulation, you need planning and control, and you need perception. And among those models, you can find similar methods that can be shared in different domains. Of course, you cannot find an algorithm that can solve two problems because it's a very complex problem to manipulate deformable objects.
Thanks a lot. So I understand, of course, you point at the different levels of manipulation in terms of global versus local, and there's also, I think, an open debate which is very actual nowadays between model-based methods and more model-free. Like I think that's a bit also what Fanny and Farshid were pointing at. So Farshid says, I don't have a model of each person's tissue, and so it's. Are we sure we're going in the right direction in this sense? Do you know if, because there's a lot of discussion at the conferences about if machine learning methods which are data-driven can be initiated by some models, and it seems like there's not much happening, although we've been talking about this for a few years now. So I don't know if you think this is the right way to go, maybe also, and if yes, if you have some works or some laboratories which you think are doing the right thing in using model-based and data-based approaches together. I don't know if you have an insight on this, in particular, of course, with respect to these applications of deformable manipulation.
I know people doing like, as you said, like a fused method, like model-based initializing, machine learnings, and then do some work mainly on medical imaging. Based on my background in Hopkins, a couple of colleagues started doing that, and they were very successful because, I mean, in medical imaging, actually, they have some method of basically deformable, basically registration. That's the same task, actually. So you have deformable registration. You start with a deformable model and try to manipulate it to register medical imaging with the things that you are seeing. So again, if you look at the physics of the problem, we are just changing the nature of the problem. The question is different, but the approach is similar. So some people have started, I think medical imaging, I have seen good work. And it's just a matter of,
in your case?
With some tweak, not exactly, right? So I'm talking about the insight. I'm talking about the general framework. So let's say, I mean, machine learning or any other approaches. So I believe, I mean, let me say what's my opinion. I believe in like the hybrid approach, not just pure machine learning, model independent or pure model based. I think some fused approach, some intelligent algorithm that can necessarily switch between model-based or model basically independent during the task, this would be the solution. So basically, what I'm working currently partially is that I want to have an algorithm that when it's necessary, rely on the human. And when it's on, basically you realize human is making a mistake, it can switch to machine learning and vice versa. So basically these two are supervising each other. I mean, during the task. This is my belief, and it's like a human being. I mean, like two persons are watching each other, specifically, like, I mean, always I'm giving the example of the operating room or surgeons. You always have multiple people. Like there, you are not just talking about one person making a decision or something. We always have one expertise on one aspect, and people are watching each other. So something like that, if we can have algorithms that can watch human and human watching basically algorithms, like these two together, I believe would be the solution, particularly for our task. Like once we are talking about the deform, we never can rely on a machine because you know that they make a mistake and also human also makes a mistake. That's my belief.
Thanks a lot, Farshid. Is there any other feedback on this?
Yeah, actually, I agree with Farshid. Another example is, for example, when you use FEM model, finite element methods, you can still learn parameters of the model. So actually, you can adopt a model, and then you can also use machine learning in order to improve the model and to adapt to the real object. Of course, you cannot know the model of an object, and you can learn something. So I also believe in the combined approach, model-based and data-driven approach.
Thanks a lot. So I think we are out of time, unfortunately, because it would have been great to keep discussing. Yeah. Jihong, maybe you want to conclude. There will be another, well, Jihong will say this better, but there will be another panel. So you're invited, of course. This was really the one IROS organizers asked us for the talks. So it's the most urgent one, but the other one will also take place soon. So Jihong, maybe you want to say a final word?
Yes. So I think we had a really, to conclude, I think we had a really good discussion, and I really hope that we can continue, but due to the time frames, yes. So first of all, thanks everyone again for joining us today. So basically, this is the pre-recorded session that will be sent to IROS organization committee, as I said, and also we were going to also promote all 3 recorded sessions with different channels. So when it's online, we're gonna send it to robotic distribution list to ask people to look at these 3 sessions that we organized, and this is actually the first one, and it has been great. And so we are thinking also, because for IROS we have very limited time. We have, I think, 1 hour, 1 or 2 hours. They allow us to do a live session, and you will all be invited again when we fix the time. And then in that session we will gather all the speakers, so all the panel together. Then we're gonna have a fully live discussion with all the panel members and speakers. So also in this case, we are also taking a step further. We are preparing an article. We hope that we can prepare one article out of this workshop, because mainly what we have seen on deformable objects, we've seen a lot of surveys, but for us we would really like to push it to more like challenges and outlook for manipulation of deformable objects. So we are preparing an article, and we will later also invite you to, probably if you're interested, to join, invite this article together to be a, it's not a survey like, but to just to show that what is the challenges and what is the outlook, what is the promising methods that we can solve those challenges. So thank you all again, and we will keep in touch. Thanks a lot.
Thank you so much. Thanks for the invitation.
Thank you.
Very much.
Have a good day. Bye-bye.
Thank you for the organization.
Thank you. Thanks a lot. See you.